All right, welcome back to the second day of the conference. Today, the first talk is by Sergei Gukov, and we're very happy to have him here. He showed a heroic effort. There was a hurricane announced, the earthquakes, sick people.
So it's just the rain.
But eventually he made it, so we're very happy he's here with us, and he will speak about the categorical symmetries of TM theories. Thank you.
Yes, thank you, Michele. So the story behind it is that before I came here, I had to send Michele email that last week that a hurricane is coming to California. At least that's what they announced. It was category 3 or 4, and then it got decategorified, so it was just a rain. So anyway, I'll start by thanking the organizers. It's a lovely meeting. I wish I could spend more time here, and I hope I will in the future. So thank you all who put this effort into organizing it and running it. Right, so there are various versions of the title I could have given for this talk. The official one is Categorical Symmetries of T of M theories. So another version of the title could be 9 versus 10. I'll let you guess what this stands for. So another more perhaps descriptive version of title, or actually punchline of what this whole talk is going to be about. On the mathematics side, I'll talk about details. So apologies, it will be kind of a little bit about specifics and technical maybe details of partition functions, invariance, moduli spaces, where I'll be paying attention to what's called homological versus K-theoretic version. So these two versions, in some sense, will be the gist of the talk. In physics language, it will be nothing but good old discussion of Kaluza-Klein modes. So we know what these are, but paying attention to them and to their effects is going to be subtle. So usually we don't think about KK modes because they're massive, we can integrate them out, but the kind of question I want to ask in this talk is what happens if we integrate them out? So what are the effects? And point is that even on various topological or supersymmetric quantities, effects will be non-trivial. That's surprising. So then at some point I thought about putting this next to each other, but then I realized it's way too many Ks and it may not have nice connotation. So that's another version of the title. Anyway, so this will be mainly based on 2 papers with Boshan, who is here, and Dupay, and also work I've done last year with Shishmani and Yao. And it relates to various other works, some of which I listed here, but there are many more. And here I ran out of space, but in the paper, we're trying to be more exhaustive as far as giving references. So apologies if your work's on the subject and your work is related, but it's not listed here. Okay, so click it. Yeah. So when I was young, I was taught that every good mathematics talk should have one definition, one theorem, and one joke. So here is the definition. There could be many things we mean by T of M theories. In this talk, I'll very specifically mean compactification of a 6-dimensional CFT. Mostly I'll focus on 6-dimensional 0,2 CFTs, compactified on manifold Mn. In mathematics, this would be fiber integration or push forward. If you think about CFT as a functor, which associates all kinds of things to manifolds that you input in the theory, then this is nothing but push forward or fiber integration. And you can consider it on manifolds Mn of arbitrary dimension. In fact, in this talk, I'll also give you examples of small dimensional manifolds Mn, but my main interest, and actually most of interest in our second paper, which will appear shortly with Du and Pashan, is on manifolds in dimension 3 and 4. So then if you compactify from 6D on a 4 manifold, you get a 2-dimensional theory, which may have a description mathematically as vertex algebra and so on. On a three-manifold, you'll get a three-dimensional theory, T of M3, and it doesn't have mathematical description as vertex algebra, but if you do focus on, say, Gukov homology or something holomorphic, supersymmetric, you may hope that you'll get something close enough to vertex algebra, and this will show up. So then here I have lots of dots in these definitions, and this dots stand for all kinds of things. So for instance, we may use different starting points in 6 dimensions. We can use not just 6D02 CFTs, we can use 6D01 CFTs, and many of you worked on this subject, and this is of interest to us, but in favor of time here, I'll probably focus just on simplest possible thing in every category. So in particular, starting point most of the time for me will be 6D02 theory, but many of the things generalize to 6D01 context. So that's what G stands for. G is for starting point, and then there is also dependence on choices of polarization. So this is a very interesting discussion on its own, and some of us have given talks on this already. So in this talk, I'll basically suppress this entirely, and with these two simplifications, if I ignore polarization most of the time, it's going to be in addition to what I'll say, and if I'll ignore if I'll just focus on 6D02 theory, then G can be interpreted as a choice of gauge group, in quotes. But in general, this stands for a choice of 6-dimensional data, the starting point. And in fact, in every single way, today I'll try to focus on simplest non-trivial case. In particular, it means that for G, I'll take either U1, which can be interpreted as starting with a 6-dimensional theory on a world volume of a single 5-brane, or SU2, that's the simplest non-abelian case. I won't really talk about high rank, which is extremely interesting and can be done, or other Cartan types, which again is very interesting, but won't be discussed. And many of the effects that I'll try to explain can be seen already in basic examples of 3 manifolds or 4 manifolds. At some point, I'll reveal my honest motivation in the subject, which is the richness of 3 manifolds, 4 manifolds. But if you don't like all this rich world, even considering simplest possible examples, such as 3 torus or S1 cross S2, will reveal actually the punchline of what I'll try to describe today. And therefore, if we already with these simple examples, we'll be able to see important delicate phenomena, then sure enough, in more general context, when we consider the wide world of 3 manifolds and 4 manifolds, we'll see them over and over again, and that's going to be important. So again, today I'll try to focus on simplest possible instance with respect to choice of initial starting point, gauge group, and underlying manifolds. So that's what we'll try to do. For the sake of discussion of categorical symmetries or generalized symmetries, the reason to focus on these theories is in some sense that they provide a very rich laboratory for testing and understanding having this generalized and categorical symmetries at work. So we have this huge landscape of different theories, and one can try to look for the Lagrangians, try to match this generalized symmetries, and learn a lot of useful physics going the other way. So I'll try throughout the talk and highlight or emphasize points where there are good opportunities from this kind of dictionary between compactification and manifold geometry to learn something about physics, and there'll be several such instances. Now, I already said that I'll start with 6D02 theory as my prime example. You don't even need to know Lagrangian for this theory. Well, we don't know Lagrangian for this theory anyway, if G is other than U1. And even if it's U1, it's not perfect, but all you have to know is that it roughly contains self-dual 2 form. It contains 5 scalars. So 5 is naturally acted by S of 5. So this is the R symmetry of the theory. And you have to know that there are some fermions here I'm way too specific for what we need to be. I tell you that they transform in a certain representation with respect to spin cover of Lorentz group and this R symmetry. But again, this is not going to be needed. So just all we need to know is that there are, in fact, most important thing is perhaps the self-dual two form and scalar sector. So we need to know that there are 5 real scalars which are in the joint of whatever I call gauge group. Okay. Any questions so far? This is the definition. This is setup. That's where we will go. As Pashan says, everybody happy? Okay, so then I have a question for you. So suppose we do the simplest possible example. So suppose we take this Mn, the manifold on which we want to compactify our 6D02 theory to be just a 2 torus. Question is, what do we get? Is the resulting theory 4D n equals 4 superring Mills? Any suggestions? When I grabbed, the answer was yes, most of the time. After all, we start with maximally supersymmetric theory in 6 dimensions. We compactify on a 2 torus, which doesn't break any supersymmetry. We end up with maximally supersymmetric theory in 4 dimensions. And how many maximally supersymmetric non-gravitational theories do we know? Right? If we know more, or if we discover more, that would be pretty cool. We can do a lot of interesting things with them. But the answer is no. And by now, this is fairly clear, hopefully to many of you. The quickest argument is based on generalized symmetries. And again, I promise to work with simplest possible groups. So in general, the 6D02 theories have 2-form center symmetry. I'll call it C for center. If my group is U1, then center is U1. If I start with SU2, then center is Z2. And then if I compactify on a 2 torus, this 2-form symmetry replicates in several different ways. And we get 2-form symmetry with 2 1-form symmetries and 0-form symmetry. So I purposefully draw them as Hodge diamond of 2 torus, so you can recognize cohomology, where it comes from. And the quickest way to derive the symmetries is to notice that, well, use this perspective that symmetry is generated by topological charge operator, and simply wrapping this operator on various cycles of the 2 torus, you get analogous operators in 4 dimensions. So here, in the case of SU2, we have to choose polarization. So half of this will be removed. So half of this will be cut out. But in any case, whatever we do, we end up with a theory which has either 2-form symmetry or 0-form symmetry or both. And I want to point to you that 4D n equals 4 superring Mills doesn't have either 2-form symmetry or 0-form symmetry. That's it. So end of proof. So this is very slick, very quick, and shows that they're different. We'll dive a little bit deeper into this, but that's already kind of indication that they cannot be the same, that the symmetries are simply different. So if in this audience we care about generalized symmetries, this should be basically a clear-cut proof or argument that they are not the same. Yeah.
So, I mean, because you told us before, no, there's only one theory with n equal to 4 supersymmetry, so I would expect this is n equal to 4 super Young Mills plus some decoupled sector, maybe? Or is...
no, it's more interesting, so.
It's more interesting.
It's more interesting.
Okay.
But in some sense, so a couple of years ago when we started this discussion with Pashan and Du, and we would tell people that, oh, did you know that there are more maximally supersymmetric theories in 4 dimensions? Typical reaction we would get is that we should be pushed out of the room. So maybe by the end of my talk, that's going to be the outcome. But anyway, so at least I'm doing honest reduction, right? So we started with, I mean, I want to emphasize that many of the things I'll do is starting with the U1 case is most clear in some sense. So there cannot be any like devil in details or anything hiding. It's a free theory in the U1 situation, and we have nice center symmetry there. So after reduction, we'll be comparing it not to super-Yang-Mills theory in 4 dimensions, but rather maximally supersymmetric Maxwell theory. And Maxwell theory, of course, has interesting one-form symmetries, and we all talk about it, but it just doesn't have 0-form or 2-form symmetries. That's it. Rather clear, right? So later I'll show you, I'll kind of demystify why this happens, and it will be a little bit more intuitive, but this is based on symmetries. I mean, for this audience, this should be most comforting argument. I hope it is. So this suggests that, well, we already kind of get something interesting just out of this very simple question. So let's start and try to compactify 6D theory on n-dimensional tori, Tn, starting with n equals 1, 2, 3, and so on. And what you'll see in the next couple of slides as we go further in dimension, increasing n, so we get on compactifying high dimensional tori, this distinction between what we would call maximally supersymmetric, most obvious theories such as n equals 4 super-Yang-Mills, and whatever this T of Mn is, quickly diverge. So in high dimensions, if n is small, they'll be reasonably close, but if n is higher, it will be more and more apparent that they're different. And also, if I were to increase the rank and play with other things, which I set to simplest possible values in the beginning of the talk, divergence will also get greater and greater. So this differential or effect of what I'll try to describe in this talk, this KKKK effect, it will be stronger and stronger, okay? So in the case of n equals 1, and again, let's just, as a test example, sanity check, always start with U1, simplest free abelian theory, non-interacting. So then we know what the answer is. We just reduce all the spectrum of, I told you that in 6D we have 2-form, bunch of scalars and fermions. So we reduce them on a circle from self-dual 2-form. Now we conveniently get the usual gauge field from, and its KK modes, and or KK modes of B rather, and then we get KK modes of scalars and fermions, okay? So here by this M, which is integer, I denote momentum on a circle. So that's what spectrum looks like. 5D super-Yang-Mills is basically 0 mode sector of this reduction. But then natural question, and this was original kind of suggestion, back when I was younger, and that's how I was taught this is, that we can consider instantons in 5D super-Yang-Mills or instanton symmetry and identify that with symmetry that corresponds to rotation of the circle, namely KK mods will simply be accounted by instantons in this case. So in some sense, the punchline or one of the conclusions that we want to draw in this work with Du and Pashan is that these two symmetries are not the same. So namely U1 that you could call instanton in 5 dimensions, that's a natural symmetry, that usual 0-form symmetry. That's not the same as U1 associated with rotation of the circle. I'll call it KK. So they're not equal. And one easy, so this is slightly more subtle than many things I'm discussing, but one way to kind of discuss this or convince yourself is to consider theories which consist of, say, hypermultiplets. In that case, or other multiplets, series that come from 6D01 content rather than 6D02. In that case, there may not even be a gauge group, so there may not be instanton symmetry in the first place, but there is, of course, KK symmetry. I think this rotation of the circle. So even if with this perspective, you dive a little closer in 0-2, you start seeing that it's not obvious at all that there are symmetries definitely are not the same, but it may happen that for very specific theory, such as 6D02, the charges of all the states are similar under this and this, but symmetries are different. Okay. So this begs an obvious question, which to which I don't know the answer for. Yes.
Thank you. So just a small remark. No, I think that the reason why people used to do that identification was having in mind the M theory origin. No, you take an M5 brane, you put it on a circle, it becomes a D4 brane. the Kaluza-Klein mode for M theory is the momentum on the circle and becomes the D0 brane in type 2A. And the D0 brane, D0, D4 has the right dimensionality for becoming an instanton for the 5D theory. So this inequality seems to suggest that there are more ways of going from M theory to type 2A. Is that?
I wouldn't go that that far. Possibly, but again, I think
because this identification comes from this.
Well, this identification again, I think I don't want to discuss 5D case in such great detail. That's why I pose it as a question. And I think what I was going to say next is that we should. I want to open this for discussion, but probably after the talk, because it can go for a long time. And I think this is a rather delicate question. We spent a lot of time on it. And I have to say, even my personal reaction at this stage is, it is kind of surprising and interesting. But there are lots of, it's, right. So it's simple enough that we're dealing with just circle reduction. We didn't even go very far. And that's on one hand is simple. On the other hand, we're dealing with all these very strongly coupled dynamical questions, which involve either M theory or 6D or 5D. So that's why it's a little hard in that sense. So in fact, like I said, if we go further on more circles, it will become more apparent easier. So this case is becoming slightly more degenerate and subtle. So my personal take currently, again, you can ask Poshan for his opinion and we can all discuss it, is that there are two symmetries. It may happen that for very specific theories, such as fibrane theory and M theory construction, states are equally charged under this two. That's why they're hard to distinguish. But even that, we are not entirely sure of. So that's I think, my most conservative or current understanding of the setup. Whether there are more reductions from M theory on a circle, I don't know. I suspect might be if we try to turn on backgrounds in non-trivial. In general, like I say, if we start from 0, 1, trying to generalize story actually sheds more light on the issue. Starting from 0, 1, it becomes apparent that they're not the same, first of all. And if it's true that for one special theory, the charges coincide, then clearly it cannot be for all theories. It's only for one special one, such as 6D02, there might be this coincidence. Right, so anyway, and then we'll generalize it in many other ways where it will be more apparent. So here I pose a question and offer you another kind of food for thought. So many people worked on it, of course. So this is very long-going discussion in the literature. And I don't think this question was ever raised clearly because people try to immediately jump to clumping it and identifying not only charges, but also the symmetries. And we definitely think or disagree with that. But to make it more interesting, again, I invite you to think even about a Billion case. So it's a free theory. We already just discussed the spectrum on a previous slide. There is no mystery about it. We have tower of KK modes. And in one case, we have these fields phi m and psi m with any value of integer m. So how would you account for these fields in 5D superring mills? So they have to have masses proportional to m and so on and so forth. So that's, again, as far as I know, has never been discussed carefully in the literature. I would love to hear your thoughts, or we would love to hear your thoughts. And I know that Ken, for instance, probably thought a lot about this. So I look forward to discussing this further. But for simplicity, again, let's continue. And as we increase n, the issue will become less confusing. It will be, in some sense, things will start diverging quicker, and it will be easier to see the gap, the difference between, say, T of T2 and 4D superring mills. So I'll do the same thing. We'll start with U1, and we just count KK modes. In this case, our scalar fields and psi's will be labeled by two integers, which represent momentum modes on two circles of the torus. So that's not too surprising. What's interesting is that among reduction or modes that we get by reduction of the B field, we now get group valued scalar. So remember, we have 5 original scalars, and now we have all of their KK modes. So now in addition, we get the 6th scalar is born, and it's group valued. So if I start with U1, my group is U1, and it will be circle valued. So this scalar is not quite the same as 5 other guys. That's why we still have in T of T2 SO5 R symmetry rather than SO6 R symmetry. So now we're learning that, well, first of all, not only generalized symmetries, 0 form, 2 form, and 1 form symmetries are different, but we're also learning that R symmetries are different in these 2 theories. And in a second, we'll learn that their moduli spaces are different. So in fact, this is what this picture is illustrating. The Coulomb branch of 4D n equals 4 superring mills with gauge group U1 is just a plane, usually called U plane or plane of Coulomb branch with U. In SU2 case, it looks like this. It has its elliptic fibration with one singular fiber, so it's a complex plane with 1 point in the origin around which monodromy is -1. Whereas if you start with T of T2, you would expect that first of all, monodromy should be +1, and this matches naturally or more naturally to the following situation. So in the U1 case, we already saw that there is one compact scalar. So if G is U1, my Coulomb branch would be a product of a circle and R. So remember, there are a total of 6 scalars. In T of T2, there is 1 periodic and 1 non-periodic, which make a Coulomb branch. 4 other guys make what could be called Higgs branch. So here, the Coulomb branch would be C star. That's the same as S1 cross R, right? And what happens in SU2 is that we just mod out by Z2 symmetry. So that creates 2 fixed points of the form C mod Z2. So the picture looks kind of like this with 2 interesting points. Monodromy is -1 around each one. So this thing looks like kind of half a cylinder. So I can erase half of the picture. And this would be the Coulomb branch for SU2. That's what's shown on a figure. So you can basically get it like this. It's asymptotically a cylinder. It has monodromy +1 as expected, and it has 2 interesting fixed points, which each of which looks like 4D n equals 4 superring mills for SU2. So there are basically 2 copies of 4D n equals 4 young mills for gauge group SU2 on this Coulomb branch, and it's clearly not the same as just 1 copy. So now we answer your question in more concrete detail. So we get 2 theories, but they're not decoupled. They actually talk to each other through the moduli space. They actually see it as 2 different points on moduli space. And note that I just did SU2. If you were to do SUN or other groups, story would be much, much more interesting. And we just scratch the surface, right? But we already start seeing the difference. We already, from here, we see clearly what's going on. We see that moduli spaces are very distinct. In fact, it's periodicity of the scalar, which is responsible for both 0 form and 2 form symmetry that we talked about. That's it. That's the whole point. That's why by naive reduction of 2 form symmetry from 6 dimensions, we got this conclusion about 0 form and 2 form. And it's clear that it's absent in 4D n equals 4. Okay, any questions? Yes.
At these 2 fixed points in the Coulomb branch, you said you got n equal to 4, but is it really the same n equal to 4? There's some difference like theta angle, something like this.
Yeah, this is a very interesting question. And in the most naive form, they are usual for D n equals 4, but you could engineer lots of different distributions here with theta angles and other things. In particular, you could ask me what happens if I start gauging the 0 form and 2 form symmetry. So here, this landscape will become much more interesting. So I'll suppress it. Well, I mean, it's yes, we discuss it in the paper. You are welcome to ask me or Pasha, and later we'll tell you more about it. But for the talk, I want to go here. There is another question.
You mentioned that the R symmetry is SO5.
Yes.
So how does it act on the charges in 4 dimensions?
On which charges?
Supercharges.
Oh, that's another good question. So, right, naively, it even looks like supersymmetry algebra is different because of that. So it's actually not quite. So that is less exciting or less mysterious. But yeah, so that's another issue I'm gonna just sweep under the rug. In view of time, there are many more things I want to cover, but very good question. So we start seeing originally I mentioned that, oh, this higher form symmetries are different, but now we start seeing that lots of things are different. The supersymmetry algebra looks a little bit different, even though again it's close enough to usual, but our symmetry is clearly different. And it all has to do, that's the only punchline, that's all I want you to take out of this talk. It all has to do with periodicity of some scalars. The fact that now they are group valued rather than Lie algebra. Yeah. Yes.
So when the scalar is periodic, the theory is also not conformal because just from like the dimension. So does the difference still persist when the volume of the torus shrinks to 0?
That's right. So that's why right. But for T of M theories, it's going to be important. That's where we're heading. That we distinguish the limit of manifold Mn being 0 volume versus non-zero volume. So it's okay if it's collection of such theories on the same moduli space. It's still more useful information than trying to take the limit of 0 volume, where indeed something would degenerate and decouple. So indeed, I can imagine, and that's exactly what happens. If I try to take this circle to 0 volume, or in this case, the torus, we'll basically effectively focus on just one copy here. Yeah. And the other goes off to infinity. But again, this is very singular limit. What I'm trying to say is that we'll lose some information.
Naively seems like this zero form symmetry is kind of like the center symmetry of a zero form gauge field, which is this compact scalar.
Yes, that's exactly it. That's exactly it. And my point in this talk is that we can't ignore this. For example, if I want to know what the spectrum of my symmetries is, as we did in the beginning, by just reducing two-form symmetry on various cycles of the two torus or manifold Mn more generally, we will get some answer. And my point is that for Dn equals 4 supreme Mills, in this case, is not going to match the answer, and for a very good reason. So we have to keep it if we want to stay with topology of Mn rather than some degenerate limit of this manifold. Well, we have to keep everything. Very simple. Okay. So then, again, if you go to 3 torus, it becomes even more apparent. So I continue with first U1, then SU2 is going to be roughly Z2 quotient of that. With U1, first of all, we get one more periodic scalar from yet another circle of the 3 torus. But then in 3 dimensions, gauge field itself, especially if it's abelian, can be dualized to yet another scalar. So now I get 3 periodic scalars. So they can be combined with my 5 original scalars to a total of 8, which is the right number. But out of this 8, 3 are periodic, 5 is non-periodic. So my moduli space is C star cross C star cross C star cross C. So 3 copies of C star. And once we quotient by Z2, we create 4 C4 mod Z2 points, each of which individually looks like maximally supersymmetric 3D superconformal theory that we know and love, namely a ABGM, in this case of type A1. But they all distributed in this moduli space, and there are a total of 8 of them. So this number 8, if I have enough time, will show up again, and I just want to record it. Okay? So this is a simple generalization. So as you can see, the number and distinction is growing very fast as I increase dimension of n. That then instead of single ABGM theory, we now get 8 of them. Okay? So I leave as a homework another example, so you can do for yourself. So I reached a case of 3 manifolds, Mn being a 3 manifold, and that's where I'm going to stay for the rest of the talk. So I invite you to consider another example, S1 cross S2. I said in the very beginning that they're all very simple and similar, so you can do analogous analysis. You'll again see interesting features. But here I want to make a digression for next 5 minutes or so. First of all, tell you that kind of illustrate the richness of this class of theories, how many they are, and how poorly we understand them. So there is a lot of work needs to be done in this department. And I'll also try to reveal my own original motivation on the subject, which is more mathematical. So if you like mathematics, then next 2 or 3 slides will be comforting to you. If you don't like mathematics, feel free to do something else. We'll come back to physics in 5 minutes. So one of the points here that I mentioned on the slide is that there will be lots of these manifolds labeled by knots. In particular, there are so-called zero surgeries on knots, all of which have the same homology as S1 cross S2. So roughly, they look like S1 cross S2 homologically. So therefore, reduction of these generalized symmetries and so on will be extremely similar to your homework. In all of these cases, what you find is that this 3D theory has very rich moduli spaces, which is roughly illustrated here in this poor cartoon. It has several branches, abelian, non-abelian branches, and so on. In old days, when we studied these theories more than 10 years ago with Tudor and Davide, we already knew that it's kind of important to include all the branches. In our description using triangulation, it was describing only like half of the theory. So in this talk, what I'm trying to explain is that even if you include all the branches, what actually matters is topology and asymptotic geometry of this moduli spaces. So in particular, this periodicity, for example, of this cylindrical type Coulomb branch is essentially due to KK modes and keeping them rather than not keeping them and trying to focus on just 4D n equals 4 super conformal point and in one of these points. So global topology and geometry is essentially the important point I'm trying to emphasize in this talk, even if you include all of the branches. So this topological geometric aspects of moduli spaces are important and can be observable in some quantities. So what is the zero surgery and where the richness of these 3 manifolds comes from? So many people who study knots not for the sake of knots. Knot theory is rather niche subject in low-dimensional topology, but many low-dimensional topologists are interested in knots because this provides actually gateway into really deep questions in low-dimensional topology. So the starting point is that first, given a knot and some rational number, say P over R, you can construct a 3 manifold labeled by a knot and this data using surgery operation, which is basically removing the neighborhood of a knot and gluing it back, taking into account this value of P over R. So among all possible values of P over R, there are some which are more special than others. So one is infinity, and this is basically where you take out something and glue back without doing anything, so you get back a 3 sphere, so that's not very interesting. The opposite extreme, the 0, is actually more interesting. And in low-dimensional topology, the 0 surgery plays a very important role, and that's what I want to focus on. But first, it plays a role in what's called property R. This is a very important theorem, used to be a conjecture, proved in the 80s by David Gabay, saying that you can identify a knot, the trivial knot, by its 0 surgery. Namely, that's the only knot basically which has S1 cross S2 as its 0 surgery. Then David himself actually proved that the same is true for trefoil knot and figure-8 knot using fiberness of these knots. And this later in 80s and 90s generated a whole slew of all kinds of conjectures and generalizations. So low-dimensional topologists really love 0 surgeries. We care about them because they encode a lot of interesting information. This is a very rich world. So for instance, generalizing the statement that you saw on the previous slide, people including Rob Kirby conjecture that if you have this, if 0 surgeries give you same manifold, then knots should be same, or in this case, equivalent using so-called concordance equivalence. So this turned out to be false because you can easily construct counterexamples with playing with orientation. Another iteration of this conjecture then was that up to orientation, the same statement. So this became interesting because another very deep and important conjecture in low-dimensional topology called slice ribbon conjecture, if that's true, and we don't actually know if that's true, even up to present day, we're completely ambivalent whether it is true or false. It's one of these conjectures which could go either way. But if it is true, it would falsify this. But in any case, this conjecture was also falsified independently. So I don't know, maybe it sheds light on likelihood of this to be true or false. That's also interesting. And then this story continues even up to present day. So here are some more recent results from more recent years. And you don't have to read through the slides, but I just want to convey that many of these questions very quickly get into statements which involve sliceness of knots, ribbonness of knots. And all of these questions are about nodes bounded by surfaces and four manifolds. So the reason many people actually care about, say, knot homology or three-manifold homology and things like that, is because this provides us gateway into four-manifold topology, which we don't understand. We don't understand classification of smooth structures. We know very, very little. And that's why some of these questions, if they're meaningful or interesting, if they have contact with sliceness, ribbonness, they actually provide us contact with something very deep. So besides various generalizations of the so-called property R type conjectures, there is another conjecture that probably is more famous or more familiar. It's smooth Poincare conjecture in dimension 4. The question is, if your manifold is homeomorphic to a four sphere, is it diffeomorphic? And again, just like this slice ribbon conjecture, we don't know if it's true or false. It could go either way. But this theorem here says that it basically reduces the question to zero surgeries on knots. So again, this just illustrates that zero surgeries are very, very important. They're very crucial. And that's why examples, these baby examples that I showed in the beginning of the talk, provide useful starting point for thinking about zero surgeries. Like I say, they're all, for example, homologically of the same type as S1 cross S2, which is zero surgery on knot. Anyway, so coming back to physics, so I apologize if this was not your favorite subject. Again, my honest motivation, my own one is more mathematical, so that's why I wanted to be completely honest with you. But there is something to learn even in this world of 3D n equals 2 theories, and in the remaining time, I'll focus just on this topic. So using the surgeries, you can first of all generate lots of theories. So this is the class that Pavel and I and many others like. These are called plumb manifolds, which is obtained by surgeries on chains of unknots. You can encode the same data in terms of graphs, and that's why they're very combinatorial, easy to work with. But here in this T of M3 for this graph manifolds, this graph is not quite like the quiver. So in the quiver, the label of the node is the rank of the group. Here, since we're in 3 dimensions, the label of the node is related to the Chern-Simons level. So it still is true that nodes correspond to gauge factors, but label is Chern-Simons level. So that's easy, that's well understood. But what the edge is actually not known even up to present day. So many people have worked on it. So here I list a couple of papers, in particular, Hee-Jung Chung spent a lot of time thinking about this question, but as far as I know, the answer is still not known. And part of the difficulty is has to do with this group valued fields. So in this paper with Sungbong, Sanyuk, and Nikita Sepenko, we made a proposal that this edge type theories should have a description in terms of RG flows, starting with sigma models where chiral multiplets are valued on group manifolds. If you consider group G and its complexification, that's a Kähler manifold. So chiral multiplets can actually take values there and so on. So this becomes like a Skirmy type model. And I remind you that in fact, Skirmy type models appeared briefly yesterday. So these are models which originally started as description of in nuclear physics, interaction of nucleons and close cousins of what we now call principal chiral type models. So they were used in, by Tony Skirm, who is interesting guy. He lived in England most of his life. Then for some brief period of time, he went to Malaysia and so on. But in any case, his proposal was, let's consider fields which are valued essentially as in what we would call nonlinear sigma models these days. So in particular, if our fields are group valued, and this is something we saw in earlier part of the talk, that would still be okay in the sense of trying to have gauge group acting on the manifold. So both Lie algebra and group have G action. And we saw earlier in this talk that in the series T of M, group valued fields appear quite often. And that's basically our proposal here, that using this kind of chiral multiplets, which say for SU2 would take values in SL2C, that's a perfectly well-defined Keller space on which SU2 can act, we can construct lots of 3D n equals 2 theories, and that on the one hand should provide more meaningful description to this T of M theories in 3 dimensions for this entire class of theories labeled by graphs. On the other hand, it would be useful because this is a class of theories which we don't know how to handle. We don't really talk about SL2C valued chiral multiplets coupled to SU2. So it would be nice to compute their indices to develop this technology. And I don't see an obstruction to this. It just nobody got to this question yet. So there is some work to be done. Any questions so far? Everybody happy? Okay. All right. So then, what do we also want from this 3D correspondence, and where are these effects of KK modes or group valued fields show up? So I'll in this remaining part, I'll give you a couple more illustrations. So the 3D correspondence is useful because you can start with a 3 manifold, and by now I hopefully illustrated for you that there are lots of them and they're extremely interesting. And you can construct this 3D theory, which we understand to some extent. We often can compute its various quantities, various partition functions. And these partition functions can be viewed as interesting invariants of 3 manifolds. So far, I focused on moduli spaces of these theories, which incorporate but contain more than just complex flat connections on 3 manifolds. So that's kind of has been focus of my discussion so far, but it's actually closely related to various other quantities also associated with complexification of gauge group, some invariants which provide non-perturbative completion of complex Chern-Simons. I'm not going to talk about those guys, but I'll focus more about line operators in this theory T of M3. And back in the day with Pavel and Kumran, we call this algebraic structure MTC of M3 because this kind of like category of line operators behaves very much like modular tensor category. In general, it's not MTC, but anyway, this is a name that seems to be stuck. In some cases, it is MTC. For example, if our 3 manifold is a length space, then you just get usual Verlinde category. But I'm not going to talk about categories in this talk. I'll talk about its Grothendieck group. Namely, if you consider line operators in 3 dimensions, you can, of course, talk about their category. That's what would be in topological context associated to a circle that surrounds line operator. But you can consider Grothendieck group of this category, and that would be a Hilbert space of your theory on a 2 torus. And this very much follows the usual state operator correspondence dictionary in 3 dimensions, local operators in theories which are either topological or conformal, or in one-to-one correspondence with states on a 2-sphere, simply because you can take a point and surround it by a 2-sphere. Likewise, spectrum of line operators is well encoded in Hilbert space of a 2 torus. Just because you can take a circle, you circle a line surrounded by surface, and that surface is a 2 torus. So that's That's a version of state operator correspondence. So to learn about, rather than talk about this MTC, let's look at this Hilbert space. That's a bit less information, but still could be useful. So from the 6D point of view, so what I'm doing here is that I'm taking my T of M3, which is already a result of compactifying from 6 dimensions on a 3 manifold, and I'm looking at Hilbert space on a 2 torus. So 3-dimensional background would be R cross T2. So from 6-dimensional perspective, the whole 6-dimensional space is T2 cross R cross M3. And that's basically this top line is just what I described. We are looking at Hilbert space of this T of M3 theory on a 2 torus. It clearly has various actions. So for example, it has action of mapping class group of a 3 manifold, just because upon compactification with partial topological twist, it enjoys the symmetry. Likewise, it enjoys the mapping class group action of a 2 torus itself, which is SL2Z. And if you think about topological twists of 4D n equals 4 superring mills, which we discussed earlier in this talk, kind of view this as opposite way of compactifying, where instead of T2, we pretend that we take T2 and shrink T2 to 0 size, we would get 4D n equals 4 superring mills. That itself, when twisted on a 3 manifold, has its Hilbert space. It could be, for example, Hilbert space of Waffe-Witten theory. And that Hilbert space also should enjoy same symmetry, namely SL2Z action, because of course there is SL2Z duality and 4D n equals 4 superring mills that remains, whether we take volume to 0 or not. And it should have a mapping class group of a 3 manifold as a symmetry and so on. So it seems like these two could be closely related, right? And indeed, in early days of the subject over the years, go ahead.
On the previous slide, how degenerate or non-degenerate is the representation of the mapping class group of M3?
Right, how degenerate or non-degenerate? In general, I don't know the answer to this. I know, right, so I know some examples, but I'm not sure how, that's where I'm heading. So I'll give you answers for a very particular class of 3 manifolds in a second. And in that case, it's not too degenerate, but again, I'm not sure if it's how representative that is. So these are hard to compute. So this is more or less end of my talk. So we're not far from the end, because it's a part where more progress needs to be done. So in these cases, it will be reasonably non-degenerate. But again, I don't know how representative that is. Right. So in fact, what was appearing on the previous slides, there are two spaces. One is Hilbert space of this T of M3 on a 2 torus, or Grothendieck group of this MTC of M3. That's one thing. So that's just by definition, they're kind of equal. But then there is another thing, which is a priori not related, the Hilbert space of Waffe-Witten theory. And again, if you paid attention to Kalos-Klein modes throughout the talk, you would expect that they shouldn't be related, and that's indeed the case. But in various previous years, people, and I was one of these people, so I confess committing the sin, were kind of identifying this closely related Hilbert spaces associated to 3 manifolds. So they all look very similar, and that's not a huge mistake, and it's totally normal when there's some subject evolves that we make approximate statements and then refine. So now my whole purpose of this talk is in some sense to pay the debt of emphasizing the differences, that are not the same. In particular, as we discussed earlier in the talk, because of the KK modes on T2, this Waffe-Witten Hilbert space for Waffe-Witten theory on M3 is not going to be the same as this Hilbert space of T of M3 on a 2 torus. They're slightly different. You could also consider, for example, reduction of T of M3 on a circle and consider a twisted 2-dimensional A model with the target space being the same moduli space, basically. And that would be yet something else. It would differ by KK modes on a circle. And all of these are, in general, not quite the same, but they're very closely related. And in many places in the literature, they're often either confused or identified, which in general is not correct. Anyway, so in the rest of the talk, I'll just quickly go through this particular family of three manifolds of the same type as we discussed earlier today. Either, for example, S1 cross S2, which is relevant in four-manifold topology to surgery operation called Gluck twist. That's a 4D version of surgery, interesting on its own right. And S1 cross T2 would be a 3 torus, which again, we already discussed. That's another class in this family. So first, I want to point out that if I were to compute this Waffen-Witten Hilbert space, which is what we're trying to do with Shishmani and Yao on 3-manifold, then distinction between Waffen-Witten and Kapustin-Witten twists is not relevant, so you can actually consider either one. So this is set of fields in each case. And by going through analysis of Gukov homology, we basically prove the following theorem, that moduli space of this Waffen-Witten theory on 3-manifold of this type can be described in terms of generalized Higgs bundles. So this is not too surprising. Nigel Hitchen showed that usual Young-Mills on the Riemann surface reduces to Higgs bundle. So we have Young-Mills plus supersymmetric completion. So it reduces to some natural generalization of Higgs bundles on the Riemann surface. And cohomology of that moduli space basically gives you this Floer type homology. So you can actually compute it. You can have explicit expression for its equivariant character. That's easy. You can actually get some corollary for Gluck twist. Unfortunately, it suggests that Waffen-Witten theory is not going to distinguish Gluck twists. That's interesting topological application. But more importantly, for sake of this talk, is that what we're considering is a situation where our 3-manifold is S1 cross sigma. And what I want to emphasize, it's very different from analogous analysis if instead of S1, we consider just R. So again, the difference will be precisely in this group valued field. So we'll have one less, and that would affect moduli space, which would be a homological rather than K-theoretic version of the same moduli space. So even if we have all the branches and so on, again, the point of this talk is that this periodicity of group valued scalars is making huge difference for computation. In particular, if you compute this Waffen-Witten theory Hilbert space on a 3 torus for group SU2, you obtain the answer, which is a 10-dimensional Hilbert space. Okay, so just application of this general computation. So this 10 in this computation naturally comes as 8, which is a contribution of this 8 points that we saw earlier, plus 1 plus 1. So it's a 10 is, what I'm saying is 10 is equal to 8 plus 2. So this is different from various other instances where we consider various moduli, various Hilbert spaces associated to 3 manifolds. For example, here's one other version called Skane module. It's defined using Skane relations, and I give you definition in the bottom of the slide. That goes back to Turaev and Chititsky in early 90s. And again, a couple of years ago, there were lots of speculations that these spaces, Hilbert spaces, should be isomorphic or equal. But in this case, this Skane module for 3 torus is 9-dimensional. So that's a theorem by this gentleman. And 9, of course, is 8 plus 1. So, and then how to relate them is not quite obvious because, again, everything here is interacting. So my point, or actually the very first question in this talk was, would I get something decoupled? And it would be really nice if things were decoupled, because then I could really decouple these contributions of 9 plus 1, but everything is interacting through this moduli space, to say the least. And therefore, there is no obvious way to decouple things. And this is, again, just one manifold, but of course, we want to have something that would be understandable in general. And like I said in the beginning, I'm talking about fairly subtle effects. So the difference here is only 10%. And you can say, well, 10% is good enough. It's very close, at least if you're a physicist, maybe experimental. But imagine that you're running Nordita and your annual budget is, I don't know, $50 million or something like this. 10% is a lot, right? So I think it's important. Anyway, so to finish on a good news, yet another distinction or subtle effect along these lines where Kaluza-Klein modes play an important role. And this will be basically the last slide, or next to the last. So imagine that we consider T2 cross M4. So now I'll move on to 4 manifolds. But I'll do exactly the same game as several times in this talk already. I'll compactify in 2 different ways. If I first reduce on T2 and pretend that it has 0 volume, then I can say, oh, this could be Vafa-Witten partition function on a 4 manifold. If I first reduce on a 4 manifold, I'll get a theory T of M4, and I can compute its elliptic genus. So what people noticed is that the modular weight of these things is different. So Vafa-Witten in their paper computed for SU2 modular weight of their partition function, and it's given by Euler characteristic of a 4 manifold. And in various works involving T of M4, just by reducing, for example, anomaly polynomial from 6 dimensions, which is, we're talking about gravitational anomaly, so this is not really rocket science, there is nothing super delicate. It's usual anomaly described by anomaly polynomial, you get this number. And they're just not the same. So first you could say, oh, maybe somebody made a mistake and there should be minus versus plus in front of chi over 2. We went through this 50 times. We believe the sign is correct. But more importantly, there is just a term involving signature of a 4 manifold. So no, it's not even present here. And there is no way to get it from anywhere. So they're just not the same. So this is yet another instance illustrating that whether we keep Kaluza-Klein modes or we don't keep Kaluza-Klein modes makes a huge difference. They're not the same. So it's interesting because these modes are massive. You could say one can integrate them and everything should go away. But in the process of this integrating out, they leave some important residue, which is a different, in this case, topological invariant. The good news is that I told you in the beginning that we, at least some of us, believe that there are 2 symmetries which are not equal. And therefore, if you really take this seriously, it means that there could be a huge generalization of Vafa-Witten partition functions, and in fact, 4D n equals 4 theories, which involve basically 2 taus. And that's pretty cool because we have now more 4 manifold invariants to play with. So, and again, in one case, it would have to do with group valued field, but also various other things, Kaluza-Klein modes. In the other case, of course, the spectrum is different. So hopefully in this talk, I illustrated that KK modes are important, or K-theoretic versus homological moduli spaces play an important role and are important. Now I want to finish with advertisement of a conference, in fact, 2 conferences that we'll have at Caltech in December. So one is focused on mathematics and machine learning. The other is more traditional, perhaps, for this audience, called string data. So these days, I'm very interested in machine learning subjects, so that could be another version of the talk I could have given to you. But if you're, and I know some of you are interested in application of machine learning to either physics or mathematics, so to those of you, I hope to see you at Caltech in December. So thank you, and sorry for running over time.
On the previous slide, do you know for which 4 manifolds minus chi-half and chi-half plus 3/2 sigma are the same?
Yeah, so that's actually a very good question. So, right, so one thought could be that, oh, sign of chi is wrong, and then we should think of these 2 terms as the same. But actually, with this sign and this sign, it's even better. I believe that's what's correct, because then the difference between the 2, that's exactly your question, is a combination which in numerator has 2 chi plus 3 sigma. So this is a very important number in 4 manifold geometry. It's basically a square of the first Chern class and complex geometry version. So for K3 surface and for other Enrique type surfaces, basically for this EN manifolds, it vanishes. It's
inequality.
No, I believe Hitchin inequality has some other combination of chi and sigma.
Okay.
We can discuss this, but in any case, this 2 chi plus 3 sigma is the one that appears, for example, in cyberquitting theory very often. It's basically C1 of the tangent bundle square. A very good question. That's why, in some sense, for many simple examples, we usually start computation. I mean, very few four manifolds for which we can compute Waffen-Witten theory are known, and I include, for example, this series of EN surfaces. And for all of them, the distinction is 0. So it's we could miss that.
Does your work showing the difference between n equals 4 and the compactification of the 6D theory have an implication for ADS-CFT?
For ADS-CFT, we would run into the question that was asked earlier, because so the way to think about this T of M theories, again, probably there are many perspectives. The way I think about them, in general, this is not a single theory. It's a collection of theories. These days, it's actually also a good perspective in ADS-CFT. People like to average or sum over theories. And this is definitely what T of M theories are. So they're collections of theories that live either in moduli space or maybe sometimes disconnected, disjoint. That's what makes their study more delicate and interesting. So a priori, it's not obvious because conformal symmetry is not as manifest and so on and so forth, but perhaps there is some implication. Maybe this has already been discussed in the literature. I apologize if I should know.
Hi, yeah. For 62,0 on a surface, for instance, class S theory, we put it on in general puncture Riemann surface. Then I would think, from your argument, the theory should also have some 0 form and 2 form symmetries. And do you think that is a part of the definitions of the class S?
I don't know what the definition of class S
Yeah.
is. So in some sense, what this emphasizes, one should be careful. One should distinguish 0 limit of the surface, I mean, the 0 volume limit versus non-zero volume limit. So things may be slightly different. Just like, again, start with T2. That's a very simple Riemann surface.
Yeah, thanks.
Depending what your definition is, the answer may be slightly different.